Hello, Physics 30s. I'm going to just spend a minute on refraction in this introductory video, just to supplement the one that Mr. Paul Anderson already posted, or which I've already posted. So uh, refraction is, as it says there, it's really the change in the direction of a wave, or the bending of a wave as it goes from one medium to the next. And there's lots of really cool examples of refraction, so we'll get into those. Kind of the standard idea here, if you just look at this, is that an incident ray of light, if it's in air, say for example, if this is air and this is water, that's a very common setup. As the light hits water, the wave fronts will start to slow down, and it will actually cause a bend or a change in direction of the light ray. And so we always measure to the normal. So you can see this is the angle of incidence, that we would label this as theta 1, and this could be the angle of refraction, which is theta 2. We just use theta 1 and theta 2. Other texts might use the incident angle and the refracted angle, but theta 1 and theta 2 is pretty easy, so we tend to use that. So let me just back up here. So the idea is that the waves are moving in fronts, and if they come at an angle, you can see these purple wave fronts kind of right in this area. See, the ray is coming this way, and then the wave front is like this, but right here, right there, that part of the wave starts to hit the water, whereas the rest of the wave is still in the air. So the idea is that the part of the wave that hits the water starts to slow down, and in doing so, it changes direction. Mr. Anderson's example of a marching band walking from, say, sand onto asphalt or vice versa is an excellent example. I really encourage you to look at that, because that makes a lot of sense to me in terms of what's really happening. And then, of course, as the wavefront continues, eventually, you get down to this position. Eventually, the whole wave is now in the second medium. Okay, but initially, the wavelengths were longer. See, you can the velocities were different. So the velocity there, and you can see that the wavelength would be from crest to crest. So here the wavelength number 2 got shorter, and obviously the velocity would also get shorter. So proportionally, there's some stuff going on there that should make sense. As we look at the relationship. Let me just move over to this one. I like this one too, because it shows if you send wave fronts head on, like in this example here, then there's no angle, so there's no bending. There's no change in direction. Literally, refraction is happening because light travels slower in different mediums, okay, in glass, for example, than it does in air or in a vacuum, and we'll see that shortly. So here it's going slow, or in the glass here it's going really, really slow, but then as soon as it gets back into air, it goes back to the normal speed. If it comes in at an angle, then we see what happens down here. So they're coming in like this, and then this first part right here starts to slow down, but the rest of the wave right here is still in the air. And so finally, they all line up, and then in the glass, they're nice and close together like that. And then again, right here, you can see that the top part of the wavefront has now entered air, but that bottom part hasn't left the glass yet. So it bends again. So all of this bending is, in simple terms, what we call refraction. So the summary here is noted right here. If you move from one medium to a more dense medium, then light always bends towards the normal. That's what we see right there, okay? The blue ray coming in goes into a denser medium, it bends towards the normal. If you do the reverse, where you go from more dense to less dense, then light always bends away from the normal. If you're doing the math, will confirm that, but that's maybe something you should kind of half memorize there in terms of how light moves. Another way you can say it is noted right here, the velocity. If the velocity of light slows down in the second medium, it will bend or refract towards the normal. And if the velocity of light speeds up in the second medium, it'll bend away from the normal. So in all of this interaction, we're really dealing with, if it helps you, we're really dealing with velocity and frequency and wavelength, because we're dealing with waves. And the point that it'll be, hopefully it starts making sense here, is that the frequency does not change. The frequency stays the same when you go from one medium to the next. So mathematically, what that means is if the velocity goes down, then the wavelength has to go down, or vice versa, that they're proportional to each other. And if the wavelength can change if the velocity changes, but the frequency doesn't. So all of those play into what was discovered by a man named Wilbur Snell in the 1600s. It's amazing. Historically, the math that they understood back then was very impressive. But he gets full credit for looking at how light bent in water and in other mediums, and he came up with this expression. This is right off your formula sheet. N is the index of refraction. We'll look at that. It's just in the very next note. So you have N is the index of refraction. And then the angles are the incident angles and the refracted angles. So incident angles would be that, and refracted angle would be that. Okay. And then, but we can also express Snell's law using velocities and wavelengths, which is what both of these are here. So I don't think these symbols are terribly foreign to you, but N is potentially something new. So let's just look at N. N is the index of refraction. It's simply calculated by comparing the speed of light in a vacuum to the speed of light in the transparent medium. And this is the simple ratio. You can calculate N, you just take the speed of light, but you divide that by how fast the light's moving in the medium, and it'll always be less than the speed of light. So, this, the velocity, that's always smaller than 3 times 10 to the 8th. Obviously, if it was 3 times 10 to the 8th, then it would just be 1, which is what the index of refraction is in a vacuum. So here I just blew those up a little bit. So here's, you will, for our purposes, we're going to use anytime you're dealing with light in air, on your formula sheet, it basically just says it's 1.00 because we're going to use that in our, if you know that you're in air, you can just use an index of refraction of 1. These are all experimentally determined values, so nothing you'd have to memorize, but we are going to use water a fair bit. And different kinds of glass. You can see there's like quartz glass, crown glass. I don't even know all the different distinctions between those in terms of how they're made or what sand is used to make those. I'm not sure, but they're different. There's lots of different kinds of glass. And then the cool one is a diamond, and we'll mention that near the bottom. Diamond is one of the most dense mediums out there that is still transparent to light, which is kind of cool. So it's basically got the highest index of refraction of any of the materials I'm aware of. So let's just look really quick, and I already started doing this just for an example. Here we have a light wave going from air to water, and it says it's at 40 degrees. The incident angle right here, that angle in there is 40 degrees. So the first question says, what's the speed in water? So what you need to see with Snell's law is it's really flexible. You can use whatever parts of it are needed. You don't have to use the whole thing. So in this one, I've already written this. I'm just going to use this part because I know the indices of refraction. They're right here, okay? And I also know the speed of light in air, which is 3 times 10 to the 8th. So really just a simple cross multiply and divide to get that set up. And what you have to note, though, is that N2 is always in the top for these expressions. Everything else is 1 over 2, but the indexes of refraction, it's always N2 over N1, so don't get that one backwards. But anyway, so yeah, here I come up with a new velocity for the speed of light in water. Okay, so it's a little bit slower. It's not like crazy slower, but it's not the same as 3 times 10 to the 8th. So the second part, or the second question, we could just do that one quickly. It wants to find the wavelength in the water. So what we need to find first of all is the wavelength in air. Okay, so using 3 times 10 to the 8th as my speed of light, and it did give me a frequency. It's 5 times 10 to the 14th. Okay, so I can find wavelength number 1. It actually winds up being 6 to the negative 7 meters. And then for me to find the wavelength in water, I don't, obviously it's going to be bending towards the normal like that. Well, that's maybe not obvious. I should say that's what we're learning. It is going to bend towards the normal like that. So I can now use the similar expression wavelength 1 over wavelength 2 is equal to N2 over N1. N2 is the second medium. And like I said, I mentioned before, the one tip here is you follow the light. So the light was in air first and it was in water second. So N1 and N2. Anyway, this, if I enter those values in, I'm going to get wavelength number 2 is equal to 4.51 times 10 to the negative 7. Sorry, I'm writing that a little bit small. Okay, but that would let me solve for question number 2. Now, question number 3, the angle in the water. Okay, now we actually get to use the part of the expression that has the angle in it. So I'll maybe do that right over here. So we can just use the 2 indices of refraction and solve for, oops, sorry, that's supposed to be wavelength, or sorry, theta 1. So make sure your calculators are in degrees, and we already know the angle number 1, which is going to be 40 degrees, and I know that N2 again is 1.33, and N1 is 1. So all you have to catch here is when you cross multiply and divide to solve for theta 2, just remember you have to do the inverse sine function before you get that, because what will happen is you'll get the sine of theta 2 is actually equal to 0.4833, and then you have to take the inverse sine of both sides. Okay, so yeah, basically we go like this. And then, yeah, then we get 28.9 degrees. I'm okay if you have to round to 3 significant digits on these, but I know sometimes the math teachers don't like that. So, but yeah, then that angle is now the angle of, it'd be the angle of refraction that's in the water. So that should make sense because we are going from a less dense medium into a more dense medium. Okay. So kind of the last thing I want to mention, or the last 2 things, is one application, which is a really cool one. It's called total internal reflection. What happens is light, as you keep increasing the angle of light going from water to air in this case, something really cool happens. As we mentioned, if you go from dense to less dense, the light will bend or refract away from the normal. And with an increasing incident angle, see, so we come in here at 20 degrees, at 30 degrees, at 40 degrees, the light bends further and further away from the normal. But when you get to a certain point, it bends so far away from the normal that it doesn't leave the water. And there's a perfect angle that will cause that, which this doesn't show. So I'm actually going to try and add that here. So it's kind of like it goes from there and it would come to the surface, right about there, and then with a normal drawn at that location, okay, something like that, then the light will bend so far away from the normal that it doesn't leave the water like that. And it will literally bend at 90 degrees. Okay, so this angle right here, theta number 2, is equal to 90. Okay, now what's important about this is this incident angle right there, theta number 1. This one is called the critical angle, because if you go past that, so you can see in the second example, it went to 50 degrees, and that one just went bing, bing, and it reflected into the water. If you go past critical angle, you will experience what's called total internal reflection. Okay, and the surface of the water will just act like a plane mirror. The light will try and go through it, but then it'll refract. Well, sorry, I guess if you're past the angle, then it just reflects internally. It's really cool to see. I almost should try and show you with a laser beam just shooting into a tank of water. You can see it. It's super obvious. So the calculation of critical angle is pretty straightforward, because all we're basically assigning is that the theta number 2 is going to be 90. That's the catch. And so if you go past that, it's just internal reflection. So here I've summarized it right here. To calculate the critical angle, we just use Snell's law, but we make theta number 2 90 degrees. So let's actually calculate that quick, because we are dealing with water, and I don't know, this example doesn't show what the critical angle is. So all we do is, let's just solve for it right now. N2 is 1.33. That's, oh, I'm sorry. Let's back up. This is why I needed to do this. So in this case, N2 is going to be 1. You see, we're going out of water into air. So the first medium is 1.33 this time. Oh, getting a little carried away with my 3's. So what we do is we don't know what theta 1 is. So that's our unknown. That's the critical angle. But theta 2 is going to be 90 degrees. The refracted angle is 90. We're looking for the exact critical angle that will cause that refracted angle. Now, if you remember from any of your math, the sine of 90 is actually just 1. That equals 1. So that's kind of nice. So then what we do is we basically go 1 divided by 1.33, and then we have to do the inverse sine of that, okay? And we end up with an angle of theta 1 should equal, I think it's 40, oh, there it is, 48.8, I guess, if we go to 3 significant digits. And what's interesting about that is, come take a look. So 48.8, if that's what our calculation is, look at that. It's just under 50, okay? So I mean, obviously in the initial drawing it was between 40 and 50. We didn't know, but we just figured it out. So just shy of 50 is where the critical angle happens, and then anything past that will be total internal reflection. So in terms of refraction, those are the types of questions that you would answer with Snell's law. And from a practical point of view, I just included these extras because they're just cool to talk about. I guess let's just do each one really quickly. If we look here, if you look into the water at an angle and you see a fish in the water, if you extrapolate the ray of light or your line of sight, the fish won't be there, which is really crazy, because what you're seeing is light that bounced off the fish and then it bent away from the normal and came into your eye. And so the fish is actually lower in the water than he appears, which is really cool. So I guess basically if you're spear fishing, you'd have to account for that. That's what I always think of. But if you get right above the fish, then yeah, that's exactly where he is, because there's no bending of light. just the reverse for the fish. The fish can actually see quite a wide range because rays of light are coming in and then being bent to his eye. So in the reverse, if he looks up at the surface of the water, I guess you could do it too if you're a scuba diver or whatever. You're near the surface, you can actually see um, you can see quite a larger cone, I guess. Um, so another one, diamonds. Diamonds are really cool. You uh, Diamonds or jewelers understand this critical angle aspect because it's different for different mediums. If you're cutting rubies or sapphires or other gems, they have different indices of refraction, and so you wouldn't cut them at the same angle. Diamonds are the most dense, and so you can see here that if you cut them too shallow, then the rays of light will actually make it outside the bottom and they won't internally reflect, because the best diamonds, or at least the best cut diamonds, they look dazzling. If you've ever seen a real diamond, it just seems to sparkle like crazy. And the reason for that is because light is entering the diamond and it's internally reflecting and coming back out right at you. And when they're cut the right way, that all of the light can be, I mean, in theory, I guess you could almost try and trap the light. You could get it to kind of bounce around a bunch of times, bouncing off different angles, and then finally come out. So I know when I was a university student, we always joked about a material called zirconium, because zirconium is basically just a really reflective metal, and jewelers could get away with fake diamonds by cutting a diamond or cutting glass, just not diamonds, but cut glass in the same shape as a diamond. But then all they did was they took zirconium and they coated the bottom of the diamond with it, so that it acted like a plane mirror, and then the light would just come in and bounce out and it would look just like a diamond. So kind of a fancy little trick. But we learned about that in the when I was at university. I thought that was kind of a funny application. So another really cool one is fiber optics. It's a common method for delivering internet these days, at least for a land-based internet. And what's really clever here is if light rays will not leave the glass, because in a small diameter, uh, there's not enough. It will just keep internally reflecting as it goes through the glass. Obviously, if light was shone straight at the glass like this, it would go through it, slow down a little bit, but then it would keep going through. But if you send it, at these lateral angles, even at any angle you could kind of get it going into the glass, it will just internally reflect and it'll bounce around and go all the way through, even if it curves or whatever. So that's based on internal reflection. Okay, the or for a fiber optic. So the last, this is an important theory concept that you need to make note of. You'll see it again in the review at the end. Isaac Newton was the first to discover that light was made of multiple colors. And he found that out by shining white light through a prism. And what he was observing was refraction. As it turns out, each color of light has a different wavelength. And so that means it's very, very subtle, but what it means is each ray of light will then travel at a slightly different velocity in glass or in, well, whatever medium it's passing through. So the larger wavelengths experience a change, a lower or less of a change in their velocity than the shorter wavelengths do. So red refracts the least. Okay, so if you look at this, red comes in and then it doesn't. I mean, we could draw normals and look at every one of them, but what you need to remember just simply is that red refracts the least and blue refracts the most. And if you watched one of those earlier videos, I always smile when I see this. You see that color purple? That doesn't exist. Not in white light, sorry. White light does not produce purple. You have to have overlapping, red and blue, of course, to make purple, but it still kind of creeps in. It's just sort of a kind of a fun anomaly to catch. But so you need to know that red refracts the least and blue refracts the most. And there's where you get Roy G. Biff, and we'll see that happen. Actually, we'll see patterns like that moving on here. So, as noted, violet depends again on your reference. See, here we have a reference where violet is from 400 to 450 nanometers. If you remember, I wanted you to roughly remember that violet was about 400 and red was about 800. Okay, so if you kind of remember that range is sufficient for the kind of, or the range of wavelengths that you need to know. You have to have those memorized for visible light. So again, here's another picture, and this part emphasizes the difference in velocities. So yeah, so like red has a really big wavelength. So in the new medium, it would travel faster, and therefore it would have less of a change, whereas blue has a really small wavelength. Okay, so I guess we could say it this way too. You could say that blue has a smaller wavelength, and so the velocity would be less. Okay, if that helps, just thinking about it mathematically. So it refracts, it'll refract more. And so yeah, the last just kind of fun example is binoculars. I always love the examples that you see in movies, like the old pirate movies, where you get you see one of these guys here, where the pirate will pull out his or his spyglass, and basically there's one lens at this end, and then there's another lens at that end, and you have to get them really far apart in order for the image to produce in your eye nicely. But they can get kind of long, and especially if you're trying to see things at a great distance. A modification arose over the years in terms of, once we understood refraction, then we could make binoculars. And binoculars actually make it so that you don't need such a huge distance for your spyglass to work. And we shorten that distance by using refraction. And there's two types. If you're familiar with binoculars, there's two types of prisms or glass prisms that are used to shorten that distance and enable you to actually see things far away. So they're called, the first one are called roof prisms, and the other ones are called poro prisms. But if you've ever seen pairs of binoculars, I actually have a pair of one of each of these. They use the same technique. So here, if you take a look at sorry, I'm bringing these up here. We'll look at the roof prisms first. So the light comes in, the light will come in here, but then it will enter these prisms, and it actually it follows a certain path and then goes into your eye. And that pathway is indicated down here. So you can see this dotted line coming in. Here's the objective lens. So light would come in right here. There's no refraction here, but in here it's internal reflection. And then it internally reflects again, but then it jumps an air gap and then goes into this second prism, which internal reflection, and then finally out into your eye. And look at all of this distance that we were able to cover, but in a confined space because of internal reflection. The poro prism works in a similar fashion. It basically uses two triangular prisms, and look, you can see here the internal reflection that happens. So again, up close, it's pretty easy to follow. So if this was the objective lens, I guess it doesn't matter. It's going to come in straight here, but then internally reflect here, internally reflect, leave the first prism, go into the second one, internally reflect, and internally reflect, and then come back out. So that is just a simple example of refraction. I hope you guys enjoyed that. Anyway, I'm really fascinated by how all this works. So anyway, I will post another video on lenses shortly.